Yes.
All right. It is time to begin, and so we will do that thing. Before I start my lecture, I just want to point out that Moodle is an important part of this class. So going to Moodle, maybe. You have the Science 111, which I believe I added you all to, and is opening now. And you have the syllabus and the schedule up here at the top. It looks a little different. You see the course evaluation. Obviously, we're not doing course evaluation yet. But you have the syllabus and the schedule. So if you lose those paper copies, you have access to them up there at the top. These are some useful sites just for information. These are actually physics sites. I don't have any on chemistry or other things right now. I really need to. These are the lectures from the last 3 years. I will put up the lectures I was working on before class, but don't have the lectures for this year yet. But just at the top, you'll have the 2020 Science 111 lectures link there. So it'll link you to the YouTube playlist. You can go there and catch a lecture if you missed something. Yes, ma'am.
You have old lecture slides on there. Are you changing stuff like per year? Like is it?
Each year I update my slides in small ways.
Right.
And so I will put this year's slides on Moodle as well.
Oh, okay.
But you have the old ones there so you can look ahead and whatnot. And then the way I have this broken down, I have it broken down by sections. So the first section of this class will be physics.
I like
and
that.
So
Thank you so much for doing
we have the physics, and like I said, these are old lectures. I will actually probably move these to another location, like just old lecture section by themselves, and put the new lectures there. And then you have the homework assignment, so you can see the first homework assignment. If you click on that homework assignment, then it will show you
the homework.
The homework. Notice the red there, important, unless otherwise noted, you must always give an explanation like we talked about. And so this is something that you could, for instance, copy and print or whatever you wanted for doing your homework solutions.
And this is due what day again?
This is due next Wednesday, a week from today.
Okay, I got some.
And for right here it says due in 7 days and 6 hours. And you will have down here, instead of view all submissions and grade, you'll have a place to upload a submission. And to upload a submission needs to be a one-page PDF file. So
wait, say that. I'm so
I say if you're going to upload your submission, it needs to be not a one page, a single document PDF file.
Cool.
And you can use like the photocopiers in the library or in this building to scan them to a PDF and email that PDF to yourself if you did them on paper. So if you have questions about how to get them to PDF, try to make sure you do get them in a readable fashion. A lot of people use an app on their phone, and oftentimes it's really not very readable, and that makes it hard to grade when you can't read it. So try to make sure what you turn in is readable.
What if we write it all on a Google Doc or a Word?
And then save it as a PDF and upload it. Yeah.
Yeah, I was thinking.
It's just, sometimes it's hard to do that. Okay, I just wanted to make sure I covered that before I got started so we don't have people like, I didn't know Moodle was important. I didn't know where to find anything on Moodle. Okay, so today we're going to actually start talking about physics. What did we talk about in class on Monday?
The scientific method.
The scientific method. That was the thing we focused on. And so here's the scientific method, just as a refresher, the one that you actually have to know, the one that's going to be on the first exam and the final exam.
Are these going to be on the quizzes?
Remember, the quizzes are based on your questions.
Oh, right.
And I returned I of course forgot to bring the PTQ forms back with me, but I returned them on Moodle. So you have a PDF copy. If you go on the Moodle page and scroll down to PTQ01 and you click on that, then you'll have a place where you can see the feedback file, which is your graded sheet that you had turned in. And remember, if it's got the little red thing in the corner, what does that mean?
That means we'll be on a quiz or test. Yes.
It will be in the database for being on a quiz or a test. It's not absolutely going to be on them. And so, I will give you back the paper copies. I just forgot them in my office, but you still have them on Moodle right now. So you have the digital copies right now. No. Things to do this afternoon.
And
Yes, ma'am.
Annabelle is currently making a Google Doc so we can all upload them on there so everybody can see.
Yeah, I'll send it to all of us.
It actually makes me happy that you're organized and working together, just so you know. Okay, going to newer material. Now remember, we're doing physics. Physics is my area, so it's the area I'm most familiar with. We're starting with Aristotelian motion. And Aristotle, in talking about motion, he described motion as one of two types, either natural motion or violent motion. Natural motion is motion that things do naturally. And so Aristotle noticed that if I take something like this cup, for instance, if I just let go of this cup, what does it naturally do?
It's gonna fall.
It's going to fall. So that's natural motion. It has a natural location. It's apparently on the ground. And if I make it do something else, so I pick it up, I did violence to it. That's violent motion. And exactly, that's unacceptable. Similarly, if I have these pi tins sitting here, that's natural, right? That's what they want to do. If I push them and I make them slide, that's not what they want to do. So what are they going to do?
Violent.
I did violence.
Oh.
And what are they going to do if I do that violence?
They're gonna just slide.
They slide, but then they stop to get back to their natural.
Them.
Oh, you're too advanced for Aristotle.
Oh.
Girl, stop, man.
So Aristotle said its natural motion is to be stopped. So I did the violence, and then it came back to its natural motion. So that's Aristotelian thought.
Right.
But then we have Galileo Galilei. And Galileo Galilei said, I think not. I think Jessica, who should be off her phone, is on the right path here. That it's not something like, well, it just has a natural motion. And so, going back to Aristotle, one more thing before I talk about this. Aristotle said that, everything has a natural position, but not everything's natural position is on the ground. For instance, now he didn't have helium balloons back then, but if you had a helium balloon and you let it go, it wouldn't fall to the ground. What would it do?
Go up.
Go up. And so Aristotle said that you have 4 different elements. You have Earth, and the natural position for Earth is on the surface of the Earth, or down below. And then you have water. The natural position for water is on top of the Earth, because we see ponds and streams on top of the Earth. And then we have air. The natural position for air is above water. And finally, we have fire. When you have fire, the flame goes up.
Yes.
And so its natural position must be somewhere up above air.
So can a violent force act upon fire?
Yeah,
Since it
you
goes
can
up and
hold
down?
fire down. That would be,
Oh,
doing an act of violence.
very violent.
And so he said that everything is made up of certain varying amounts of these materials. So he would say that this golf ball has some of all 4 probably, but mostly earth. This cup has a little more air maybe. And so if I drop it, because it has more earth, it wants to get to the earth more. And so the ball hit the ground first because it has more earth. That's what Aristotle said. But Galileo said, no, it's something different. Going back to what Jessica was saying, there's something else at play. And so, as you notice from my example, the golf ball hit the ground before the cup did. And so Aristotle said that's an obvious reason to know that the golf ball falls faster. Aristotle actually, as I understand it, he said that they fall with a constant speed that's proportional to how much earth they have and the other things. So this has more earth, it falls at a faster speed. So Galileo's famous experiment, which he may never have done, it's something he used to explain his concept. He may or may not have actually done the experiment. He did a lot of experimentation with inclined planes. That's taking boards like this, tilting them and rolling things down to test his theories. Because remember, the scientific method is all about testing. Galileo is really considered the father of the scientific method because he tested his hypotheses to see if they made correct predictions. So This one here, the Leaning Tower of Pisa, the idea is he had two spheres, but one was heavier than the other. So let's say one is twice as heavy as the first. According to Aristotle, that means one has twice the earth of the other. The one with twice the earth should fall at twice the speed, according to Aristotle. And so the experiment would be, well, if I drop them both, and one has twice the amount of earth, according to Aristotle, it should take half the time before it hits the ground because it's going twice as fast. But Galileo thought it was different, and sure enough, he dropped them. And what do you suppose was the difference in the time it took for them to fall from the top to the bottom? If you'd actually done the experiment.
Yeah.
What would you think?
Not a lot.
Not a lot of difference between the two, roughly the same.
Yeah.
So we're going to watch a YouTube video, which I already have queued up, so it should be faster to watch it, of this experiment, Galileo's proposed experiment being done, I'm genius, being done on the moon using a feather and a hammer. Now on Earth, you saw that when I dropped the golf ball in the cup, there was a noticeable difference. And if I dropped a feather, what would the feather have done? It would have taken its jolly old time. But according to Galileo, that's because of air resistance rather than it being a natural thing. So here is an experiment to see if Galileo was right, done by, I can't remember which astronaut, on the moon. And why do I, okay. I don't know why I have 10 seconds of wasted time.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch the. A good picture there. It's got beautiful picture there.
Beautiful picture.
Well, in my left hand I have a feather. In my right hand a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. And the feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
Yeah, how about that? Just because you can test Galileo, right?
That's right.
I always say Galileo, but you notice he said Galileo. And who am I to?
Pop it back to NASA.
That's right. I don't have that kind of clout. So I said clout.
Oh, okay, cloud. I heard cloud.
I heard cloud. I just wanted to make sure.
Okay, so the point here, yes.
So if you
Vanessa,
shoot,
right?
yes, if you shoot a gun in space,
Mhm.
the bullet, it has no weight, but it has mass. That's what you said. So, is it going to accelerate in speed, or is it going to stay the same speed until it hits something?
Let's make sure we get a correct simplified model here. Right, simplified because reality is there's always some very tiny ways. But if you were somewhere with, this is the only mass anywhere within reason, and if there's no air resistance, it will just keep going at a constant velocity, which we haven't learned the word yet, but that means a constant speed and the direction won't change forever, since we eliminate anything else.
So it won't accelerate.
It won't
Unless
accelerate.
something makes it.
Okay, the point of this experiment was disproving Galileo and showing that it's not that we have a natural motion, but in fact we have this thing we call inertia, which gets to what Vanessa was asking about. Inertia is the property of an object just staying in constant motion. So I'm not talking about violent motion or natural motion. Constant motion unless something forces it to change. So if you had a bullet out in space and there's nothing around to force it to change, it will simply keep going in a straight path at a constant speed. Now, I haven't defined speed yet for physics class, but you do know what speed is. You know, you've been in the car. So that's the concept of inertia. And so notice here, in the absence of friction, what Jessica invoked earlier correctly, no force is necessary to keep an object moving, whereas Aristotle said you have to do violence to keep it moving because it's not the natural state. So, what is inertia? Not friction. Yeah, inertia is the name we give to something traveling with a constant motion unless something forces it to change. Not at rest, but just constant motion, whatever its motion is.
So that doesn't really happen on Earth due to gravity.
Right. Due to gravity, we always have something that's trying to pull us down. But at the same time, if I have, we have the tracks that we use in lab. So if I have a track and it's horizontal, gravity's trying to pull down and the track won't let it go down. If there was no friction at all, if I pushed the cart, it would just keep going straight horizontally and never slow down if there's no friction. But not just almost. It's impossible. But it's something that we can think about. Now, mass is the name of the property that we use to measure inertia. The more mass something has, the more inertia it has. And I just introduced inertia as a property of not changing motion unless something forces it to do that. We call a thing that would force it to do that a force. You're tricky this way. Jessica already has her question. And it's appropriate. I have to make sure, because it needs to be based on something I said in class. I was like, how much have I said in class so far? Well, it has to be on something I said in class. Okay, so how can mass be a measurement of this property? Mass is a measurement of how easy it's going to be to force it to change. Something that has a low mass, it's going to be easy to force it to change. Something with a large mass, it'll be hard to force it to change. And so the picture here with the anvil, let's suppose somebody tosses, I won't toss the golf ball actually, because if you miss it, it actually would hurt. No,
I'm just kidding.
I'm gonna do it.
That was
Well, I'm used to that from my brother, so
It's fine.
I'm used to being banged in the head with a golf ball. No, if I throw the golf ball to you and it hits you in the chest, it'll stop pretty easily. It won't hurt too bad, right? If it hits you in the head, it might hurt a little more, but it stops pretty easily. But if I took an anvil and threw it to you at the same speed, and the anvil hits you in the head or the chest, it's going to be a lot harder to stop, right? You know that.
Wait, what's an anvil?
An anvil is a big piece of iron that they use to pound stuff on. I'm sorry.
you've probably seen it in cartoons being dropped on someone's head.
That's true. Like Wile E. Coyote.
Okay, that makes sense now.
Okay, the bottom line is anvil is something that is really heavy. And so now I just said heavy, but before I said mass, there is a relationship between mass and how heavy something is.
Yes.
So, for a practical sense, on Earth, you can think of the two as analogous, but they're not really. Because if you are somewhere that has no gravity, there's no weight. Doesn't matter what the mass is, it has no weight. But it still has different masses, and the anvil would still, if you are out in space and an anvil comes flying at you, it's going to be just as painful to stop it as it would be here on Earth. So mass is a measurement of how much inertia it has. Another way we talk about mass is a measurement of how much stuff is present. The more stuff present, the more mass. There's a whole lot of me here. Hence, I have a large mass. All y'all have smaller masses because there's less of you.
There's no guarantee there unless we have a scale.
Dang, she called
This
you.
is true. You don't know my weight. You don't know my weight.
I don't know
either.
your weight, but I am really confident you weigh less than Jessica.
You don't know.
I'm really confident.
I got big arms.
And let the record show I did not call anyone here big except for me. Okay, so this is just a funny little example. If you had an elephant on roller skates and you wanted to make that elephant move, would it be easy or hard to make the elephant move?
On roller
I mean, it's
skates?
still
On roller skates, yes.
Easy if it's on roller. Well, I mean, it'd still be hard to push, but it'd be easier than if it wasn't on roller.
Okay, it would still be hard to push, but it would be easier than if it wasn't on roller skates. Why would it still be hard to push if it's on roller skates?
Elephants are like a ton.
Because they have a lot of mass.
Look
Yeah,
at us.
there you go. See,
Yeah.
not so hard. Okay,
Smart.
now, as I said, weight relates to mass as well. If you have twice the mass, you have twice the weight.
Twice the mass, twice the weight. Makes sense.
So,
That's weight is gravitational.
right.
Girl, look at you.
I'm a genius.
Now we have another term, volume. What is mass? Just reviewing, what is mass?
Mass is how
Mass
much
is
matter.
How much matter is present, or how much inertia it has. Both of them are correct. Technically, there are two different answers and there's two different definitions of mass. There's inertial mass and gravitational mass.
Okay, hold on.
But either one is correct, and we'll just stay with that. Weight is what we call a force. Forces are things that push or pull. And the weight of an object, if it's on Earth, is its mass times a constant.
Yes.
And so you just say, oh, well, this much mass multiplied by that constant, you have that much weight. If you're not on Earth, it's different. And if you want to be all technical, Amy and I bought a house in Hartselle, Colorado. Elevation of 9,400 feet above sea level. The acceleration of gravity is less there. So when I go to that house, I automatically weigh less.
That's great. No
Yeah.
way.
Why would you
That's
not? Why
really
would you
cool.
ever
Me
leave?
goes way myself.
Why would you ever leave? I'd be like, this is where I'm at, my lowest point, so we're just staying here
and
forever.
I would like to, but I have to.
So the higher
food
you
on the
go,
table.
the less you weigh.
Yes.
Girl, let's
I live in
Everest.
Florida, no wonder I'm
Oh. Now the difference is really small.
still a pound means a lot.
Okay.
So, okay, I'm gonna be this person, sorry guys.
Go ahead,
I'm a
Jess.
little bit confused. So mass is how much matter the object contains.
Yes.
And volume is how much space an object
Takes up.
occupies. So like this would be how much it weighs, the mass would be how much it weighs, and the volume would be how much area it takes up on the table.
Words are kind of wrong there, but I think you have the right idea, right? Because you said like mass is how much it weighs. Weighs is a force. That's the mass times gravity, so it's proportional to how much it weighs. It's not equal to how much it weighs.
Okay,
And the volume is how much space it takes up.
okay.
So you can make things have the same volume but different masses. That is, you can make two boxes that are the same height, width, and length, but one is heavier than the other. The heavier one has more mass. How is that possible? Well, one answer is one can be hollow and one's not. Another answer is one could be made out of aluminum and one could be made out of steel. Question?
So volume is kind of like almost ever changing. Like with my backpack could have more volume than it does right now, or even I could based on my jacket or my shoes.
Right. Let's take your enormous water bottle here.
Oh.
The water bottle has an internal volume of, let's guess, 1.5 liters. Is that about right? Yes, 1.5 liters. So the volume of 1.5 liters is how much space is inside this volume,
But the mass
or how much space is inside this bottle.
ever changing because of how I drink it or
Well, we have right now the volume of actual water, because there's a sticker over this we can't read, but it's about 600 milliliters right now.
Yeah.
So 600 milliliters, we haven't talked about any units yet. We will soon. But that is how much volume the water has. And the water has a specific density. That's the word on the next slide. Oops, we have a quiz before we go to the word on the next slide.
Oh my god.
Oh no, it's not a quiz that is anything
Okay.
for your grade.
Yeah,
Is
you just
testing
figured
your-
out hard path.
Is testing our understanding so that if you all understand it, we're happy, we move on. If you don't understand it, then I talk about it some more.
Sorry, guys.
Okay, so
Someone just let you know right now.
water has a constant density, that is the mass divided by volume. That's what we have those two words that we're doing. And its density is 1 gram per milliliter.
Okay.
If instead of water you had the same volume but it was iron, iron has a much higher density, much higher mass per volume, so it would be heavier even though it had the same volume.
Yeah. Okay.
Okay, let's do this little question to review what we know. So this is where you should pull out your phone, Jessica.
Jeez. Okay, my dad is like worried I'm gonna be human trafficked, so I like have to reassure him that I'm not.
We're in Nebraska. Unless you go on 27th Street, you're
Omaha is
good.
like the #1 human traffic.
It really is, though.
Okay, so Alex has your computer out. You can just type in that URL.
Clap.
Or if you have your phone and you have a like if you have an iPhone, just use your camera and look at that QR code. Otherwise, use the QR code reader, or you can type in
Okay.
the URL.
Yeah, I'm just gonna do it.
Besides raise your hand, there's no vote in progress at the moment.
You're the only one who's connected so far.
How would I know to raise my hand if my head is down?
The point there is simply that we're getting connected. You got connected. It says look up because there's no question yet. We have 3 of you connected so far. 4 of you, only 1 left.
Don't make me clap back.
I was coming for myself because I literally was like, wait, what?
She was like right after you're like,
I was not coming for you. That was not
Do you
direct.
ever stop my classmate? That's rude of you.
Me, myself.
And in your browser, you might just bookmark this because we will periodically use this.
Okay.
And I'll always use the same URL. What I do is I
Boom.
I archive the quiz and then make a new quiz with the same URL.
Four.
Jessica is to the rescue.
I got you.
Yeah,
Oh, goodness, one time I called Dr. Banks. Instead of saying Professor Banks, I said Dr. Banks, and he goes, what? And I was like, oh. Well,
Excuse me.
There was one time I called
Did
Professor.
you get her?
She's gonna try to text you.
no.
Okay.
Yeah.
You.
Okay, so let's go on to the question. Here's our question. The concept of inertia involves mostly which property? Maybe. There we go.
Waiting for next class. This is sassy. So where
How
would
do you know which one of us submitted the right answers?
I don't know. It's not personalized.
Okay.
where do we find where you put
Yay, she's connected.
our thingies that we turn in?
So does she just text A or B?
A, B, C, or D, yeah. Or 1, 2, 3, or 4. Excuse me, 1, 2, 3, or 4.
Oh, this is-
So if you think it's 4, you put 4. And then you go all the way up.
Wow.
Okay, Vanessa has answered, and here's what we have. 5 people said mass, and nobody said the others. And that's perfectly correct. Inertia is measured by mass.
So you're smart.
Your girl be freaking out over here.
All right,
Yeah, math.
so
I felt attacked.
the unit of mass now. And as of this past summer, the definition of mass has changed.
Acceptable.
Well, no, it's actually really acceptable.
Oh, very good.
Mass was the only one that had a really nebulous definition. There was a block of platinum uridium alloy, I believe it was, or platinum uridium. Uridium's not even a thing.
That is new to me.
It's platinum. I can't remember what the other one was. Platinum and something.
Huh.
Or iridium, I think.
Interesting.
Anyway, it was just this ingot, and they said that's a kilogram. And so the only way to test if you had the right definition of a kilogram would be to come and use a balance and measure against the two. Very hard to check to make sure you're correctly calibrated. Now the kilogram is, okay, it's kind of convoluted how it's defined, but it's defined on things so anyone in the world can reproduce it. But the kilogram is our metric unit for mass.
Metric unit for mass.
Yes. We call it the International System in English, or Système International in French, so it's the SI system. So a kilogram is just a unit of mass. How much mass is a kilogram? Well, this is 1 kilogram. So here, Jessica, 1 kilogram. That's how much a kilogram is. Now, what is she actually gauging when she holds it in her hand? How much it weighs, right.
The amount of gravitational pull on the object.
That's right. That's how much you can gauge by holding it. So, how much does that weigh? The weight of the object is, and I use an F because weight is a force.
I thought you were about to throw that at me.
No, don't throw.
No.
Don't throw at me either.
No.
Oh, you already had it?
Yeah, I think so.
Y'all leave them for the
So the weight I write is F with a subscript G. F stands for force. Force is a word. Of course, you know the word force. I can't force you to do anything, right? But a force in physics is anything that pushes or pulls. Like Annabelle has been studying like she told her dad.
What a thought. Sorry.
So a force is anything that pushes or pulls, and weight is an example of a force. It's the force due to gravity, and that's why I put F with the subscript G. F for force, G for gravity. And that force of gravity is on the surface of the Earth directly proportional to the mass. And that's multiplied by something else, G. And G is called the acceleration of gravity.
I was like, there's no G in the word acceleration. I'm gonna use
Yes,
There's no correlation.
you are correct on that. And you will find some things that don't seem to have correlation. Yes, Alex.
I have a question kind of for the lab. So I totally wasn't looking for the lab book to see what we'd be doing, and noticed that our assignment said don't use the word acceleration.
It did.
Yeah.
Oh, I haven't gone there
So
You'll have. Let's not worry about it right now in class, but you'll have to show me because I'm kind of
Okay.
curious about the context of
page
that.
11.
Okay, I will have to look at it.
Okay.
But G is the acceleration of gravity. It's the acceleration caused by gravity when you're on the surface of the Earth. Now, if you go away from the surface of the Earth, we can still use G, but it's a different value. On the surface of the Earth, depending on where you are, G is approximately 9.80 meters per second squared. Some places it'll
Do
be,
you have to know that off the top of our head?
no. In fact,
That's a little cheat sheet.
yeah.
Oh.
I don't care for you to memorize equations or numbers.
Then you're a
Like,
good
that's just a
person.
waste of your time. Even
I
though you can
agree with you.
memorize,
I
it's just taking time.
Right.
What I really care about is you understanding concepts and being able to use them.
I agree.
So yeah, you don't have to memorize it. And if you look here, it says 1 kilogram has a weight of 10 newtons. Now, according to what I just wrote, what should the weight of 1 kilogram be?
10 newtons. 10 newtons. Except for on the moon.
According to what I just
Because
wrote. Not what's written on the slide, but what I just wrote on the slide.
9.8.
It should be 9.8 times 1.
Oh, you right.
9.8.
So it should be 9.8.
Okay.
The textbook often says because 9.8
Oh, they
would
round
round
up.
to 10, it's going to make our math a lot easier if we just use 10 instead of
So
9.8.
do you want us to say 9.8 and not 10?
I will allow you to use either. I will always use 9.8 because I can't. It's like I feel like I'm
In
lying.
the right conscious, you just can't do that.
Yeah, I feel like I'm lying, so I will always use 9.8. But if you want to use
Yeah.
10, you can, and I won't mark you wrong.
Yes.
Oh, okay.
Now, units. Units is kind of a confusing and tricky thing. When we measure things, we have to talk about, how big they are. Like, I could ask you what your weight is. I would. And you could answer, I weigh X amount of pounds.
This is only 90.
Girl, I see it.
Yes. Beautiful.
Okay.
In one way.
You could answer in pounds. Pounds is a force unit. A pound, what's the abbreviation for pound?
LBS.
LBS for pound, LB for pound. What does LB stand for?
Light. Light bearers.
It is one of the signs of the zodiac, to help you out.
One of the signs. Libra.
Libra.
That's me.
LB stands for
Can't really
Libra.
call them Libras here.
Oh.
Because Libra is, she's got a little
Oh,
balance
yeah.
there. And it's a
Hey, Libra.
apparently a Greek word for sports. Or Greek, yeah.
Oh, no, I can't.
Latin. Anyway, so that's what LB stands for, Libras. But that is not the scientific unit. The scientific unit, the standard unit, is the metric system unit, or the SI unit, that is the Newton. So if I ask you how much you weigh, you could also answer your weight in newtons.
Oh, wow.
But let us say that you have a mass of 100 kilograms. You have a mass of 100 kilograms with a standard social gravity, you are going to weigh 220 pounds.
Say that one more time.
If you have a mass of 100 kilograms,
100 kilograms.
you'll weigh 220 pounds, or 100 times 9.8, 980 newtons. Well, if you just say I weigh 980, it's not going to be clear unless somebody's like, there's no way that person weighs 980 pounds, they must be using, newtons. Jessica.
Why do we use stone instead of pounds in European countries?
Stone is,
I've never heard of that.
well, it's 20 pounds, I believe, is a stone. And, it's going back to ancient things like, distances. I mean, we're talking about units. Let's, an ancient way to measure something. Here's a big stone. Here's 2 stones. I mean, that's literally how they got it.
Yeah.
Just like a foot. A foot would be the length of a leader's foot. You change kings, you change the foot, right?
Yeah, really? Is that how that works?
Yep.
Oh, that's
And
Oh, what if he
yard,
had a little
a yard is the distance from the king's nose to his outstretched fingertips.
that's cool. I didn't know that.
And, these are not very reproducible, right?
Yeah. But
And
still.
so things have been standardized. Now, the standard unit we use for distance in science is the meter. The meter was designed to be based on the distance from the Earth's equator to the North Pole along the prime meridian. And the original calculation, I believe, it was supposed to be 10,000 kilometers from the equator to the prime, or to the pole on the prime meridian. Now, it's not quite right because, surveying being what it was back then. But that's how the meter was originally defined. Since then, it has been defined differently. So the meter now, how long is a meter? We don't have yardsticks at all. All we have are meter sticks because, hey, it's a science lab. This is a meter, and the meter is defined based on the speed of light. So it has a very reproducible definition. You can test it anywhere. So the meters are unit of distance. Now I said kilometer, which of course we never in America, we don't say kilometer, we say kilometer. Honest to goodness, one year in my physics class, the entire year I said kilometer.
Just to see what they would do?
Huh?
Just to see what they would do? Or because,
Oh, just because I want to be correct,
oh, okay.
but I felt so foolish I stopped. So what does the prefix kilo mean? 1,000. So a kilometer, a kilometer, is 1,000 meters. And most of us are much more comfortable with miles when we drive.
Oh, you were not wrong.
I am not wrong, yes. When I was a child, the US officially changed to using kilometers. All the road signs were changed so they had distances in both kilometers and miles, and speeds in kilometers per hour and miles per hour. The idea is being, you see both of them and you start to get used to the other one.
But that didn't happen.
Americans said, this is confusing. Oh, I don't know how fast to drive. I don't know how far it is to Bakersfield. And so after spending millions of dollars to change all the road signs, they spent millions of dollars to change them back. That's why we don't use them.
Americans are very lazy.
I agree, very unacceptable.
I agree, they're lazy.
Yeah, I think now too though we
Americans-
could move back because so much stuff is in miles per hour and per hour timing that it would just be so hard for us to go all the way back. We don't have
That was what they said. This is when I was in grade school. It's recent history. If you watch Big Bang Theory, you can watch Sheldon rail against Jimmy Carter giving up on the metric system.
Oh my. Wow.
But
Cool. So you're saying the Big Bang Theory is one of your favorite comedies?
I do agree.
Same.
Yeah.
I think it has a good funny aspect.
But we need to be comfortable with these prefixes and the units.
Okay.
So even though I expect you when you're driving your car not to say, so that's 100 miles, is it? Well, I'm saying it's 160 kilometers. That's not a hard conversion.
Really? I really think it is. I really struggle with that. Yeah, because you just went from that to that, and I was like, whoa.
I multiplied by 1.6.
Wow, intelligence.
So I don't expect you to talk about distances that you travel with kilometers and that kind of thing. But in this class, we're going to use, except for when you're changing units from one to another, we're going to use exclusively meters. And then we might have a prefix like kilo that means 1,000, or centi. What does centi mean? Means 100. So a centimeter is a 100th of a meter, or a cent is a 100th of a dollar. So we have those prefixes we're going to use: distance, meters; mass, kilograms; time. Time is the easiest of the three basic units. What's the basic unit for time?
Hours, minutes, seconds.
Okay, she said hours, minutes, seconds. Seconds is the basic unit.
Yeah, okay, yeah.
And then hours and minutes are 60 times. Yeah. So on. So those are our three fundamental units: seconds for time, kilograms for mass, meters for distance.
Yes, okay, cool.
Now, if we look at the acceleration of gravity, its unit is meters per second squared. We'll get into how you have a second squared, because obviously there's no such thing as time squared in real life, right? We'll get to what that means. But then the unit, if you multiply mass, what's the unit of mass? Kilogram. Times g, unit is meter per second squared.
Right,
The unit you get for force must be kilograms times meters per second squared.
right. Okay.
And to make it easier, instead of saying kilogram meter per second squared, we say Newton. So a Newton is a kilogram times a meter per second squared.
When doing equations, how do you tell the difference between mass and meter? You just know the equation.
That's a good question. M is, if M is used to describe something like this has a property of M equals this, then M stands for the property mass. But if it's a unit, M is always going to be meter.
Okay.
Now, it can be more confusing because what about MM?
Millimeter?
MM is millimeter. The first M stands for milli, the second one stood for meter. But that's because they're a combined unit. The last part is what the actual unit is, and then in front of that's a prefix. Which I know is not unconfusing.
Yeah.
Yes, Vanessa?
I was just saying I have to go over this again. It's a lot.
That should be the same in every class, right? And I tell my son, if you already knew this stuff, why would you have to take the class?
Right.
Okay, now to density.
Density.
Density is mass divided by volume. So density, different things will have different densities, different mass per volume. What's the difference in somebody floating and somebody sinking in the same pool? They have different densities. The one who floats has a lower density. Sad truth, fat is less dense than muscle or bone. And so somebody with a higher percentage of fat is more likely to float because they have less density. Somebody with less fat, more muscle and bone is more likely to sink because those are more dense. And so each one of us has a slightly different density because we're made up of different amounts of different types of materials. And so if you take your total mass divided by your total volume, you get your total density. Of course, your volume is kind of hard to determine, but they actually do have chambers that you can stand in that will measure your volume by how much air you just.
Have you done that?
No. All I've done is you get in the swimming pool and you either put weights on or hold an empty bottle and fill it with water to measure
That
your
one's
density.
weird. I've done the empty bottle one. That one's weird. I don't like it.
Okay, but the key here, density is mass divided by volume. Now volume is how much space something takes up in 3 dimensions. So if I have myself a cube here, it has 3 sides, A, B, C, and the volume is equal to A times B times C. So if A and B and C are lengths, they all have units of meters. So if I have a meter times a meter, what would I have?
A meter times a meter.
We call that a meter squared.
Oh, right.
And if I have a meter times another meter,
Meter cubed.
meter cubed. So volume can be written with units of meters cubed. Mass has units of kilograms. So the SI unit for density is kilograms per meter cubed. Now you will note that when I was talking about Jessica's bottle, I said liters. Liter is a unit that is based on the centimeter, actually. 1 centimeter cubed is 1 milliliter. And so it is a metric unit, but it's not the base unit. The base unit would be the meter cubed. But liters can be converted, and it still is a metric, it's just not the base unit. Okay, our second woo clap question. So it is now available. The density of 1 kilogram of iron is, and now we're talking about if you go to the moon, it's going to be less on the moon, the same on the moon, or greater on the moon. What's different about the moon compared to the Earth?
There's like less gravity.
There's less gravity. G is a smaller number.
Yes.
Oh, wow. Everybody's answered already. Good job. I was actually expecting it to take longer. And we had 5 that said less on the moon, and 0 said the rest. Answer says
Less on the moon.
The survey says.
It's
Oh.
not
Uh-oh.
the same.
the same.
The same.
Because density is the mass divided by the volume. The mass, it doesn't matter. Remember, mass is a measurement of how much material is present or how much inertia it has. It doesn't matter where you are, it has the same amount of material present. And then volume is how much volume it takes up. Once again, that's not going to matter where you are. So the density stays the same. What would have been less? What were you thinking when you said less? You were all thinking the same thing. The weight would be less. That's right. Because the weight, by the way, here's the symbol for density. What is that? That's the Greek R. That's rho. And going with Alex, yeah, I don't know how R relates to density. That's the Greek letter rho, which is R in Greek. So the force of gravity, the weight, is mg, and g is lower on the moon, so the weight would be less, but the density is the same.
Wait, what is that? Force of gravity equals what?
Force of gravity is equal to mass multiplied by the acceleration of gravity. All right. I won't talk any more about forces because we have less than a minute remaining. Oh, wait, we just passed that. We have no time remaining. Have a great day. I will see you in lab tomorrow. This room, 2 p.m.
Mass times what again? Force of gravity?
The force of gravity is mass times the acceleration of gravity. Yes. Question, Annabelle. Yes. Let me actually stop the recording, just,